We are jumping right in with the technical report on DeepSeek V3.2, pushing the frontier of open large language models.
And this one is a big deal. It really feels like a milestone, showing how open models can finally start to match proprietary giants like GPT-5 and Gemini 3.0 Pro.
But not without some very serious, very specific investments.
Exactly. For the quick summary, there are really three core breakthroughs here. First, efficiency. They introduced something called DeepSeek Sparse Attention, or DSA.
And that slashed the computational complexity for long sequences.
Right. It took it from the classic and very expensive O-totally-2 down to OK, which is just critical for their 128K context window.
Which brings us to breakthrough number 2, scaling up post-training.
Yes. And I mean scaling it up massively. They poured a computational budget of over 10% of the entire pre-training cost just into reinforcement learning.
That's a huge commitment to post-training. And the third piece was about making the model a better agent.
Yeah, agentic robustness. They built this new large-scale agentic task synthesis pipeline. It generated something like 85,000 complex prompts to really hammer on the model's ability to generalize and follow instructions.
And the results speak for themselves. The base V3.2 model is matching GPT-5 on reasoning tasks.
And the high compute version, the DeepSeek V3.2 Special, is even hitting performance on par with Gemini 3.0 or Pro. We're talking gold medal level performance at the IMO and IOI for 2025. This really does set a new bar for open source.
It really does. And the paper kicks off by framing why this was so necessary. They talk about this divergence we've seen since 2025.
Right. The gap has been widening. You have open source models like Minimax and Moonshot, and they're definitely getting better.
But the proprietary models from places like Anthropic, DeepMind, OpenAI, they're accelerating at a much steeper curve.
And DeepSeek basically diagnosed why. They pointed to 3 key deficiencies holding the open community back.
The first one was architectural, right? Just the raw inefficiency of vanilla attention for these super long sequences.
Exactly. It's a computational anchor. It just doesn't scale. If you can't run it cheaply, you can't deploy it cheaply, and you definitely can't afford to do more training on it.
It's a compounding problem.
Which leads right into their second point. Not enough investment in post-training. Historically, open source just hasn't had the budget for the kind of heavy RL needed to unlock that next level of reasoning.
And the third deficiency is the one users feel the most, that lag in AI agent capabilities.
Yep. The instruction following and the ability to use tools reliably. That's where proprietary models had a huge lead. So V3.2 is their direct engineering response to all three of these.
So let's start with that architectural fix, the DeepSeek Sparse Attention, or DSA.
This is their secret sauce for efficiency. Standard attention is OLT2, quadratic. So if you double your sequence length,
your compute cost quadruples. It's brutal.
But DSA gets that down to OWs, where dollars is the full sequence length, up to 128,000 tokens, and tight dollars is just a small number of selected tokens.
So instead of every token looking at every single token that came before it,
it intelligently picks out just the most relevant ones, a much smaller number, like 2048 in their sparse training stage. It completely breaks that quadratic bottleneck.
The magic, though, is doing that selection without adding a ton of new overhead. So how did they build it?
They split it into 2 main parts. The first is called the Lightning Indexer.
The Lightning Indexer sounds fast.
And it is. It's a very lightweight brain that decides which tokens matter. It calculates a score, Godary ATS, to figure out what the full expensive attention would have focused on.
And they kept it lean by using fewer heads and FP8 precision so it doesn't slow things down.
Exactly. And its whole job is to learn to mimic the dense attention pattern, using KL divergence loss to get its outputs aligned.
So it's a fast proxy for the slow, heavy mechanism. And the second part?
That's the fine-grained token selection. Once the indexer picks the top K tokens, this part just goes and grabs those specific key value entries. You only run the full attention calculation on that tiny relevant subset.
And to get this working, they had to do some careful continued pre-training on top of their V3.1 model.
Right, in 2 stages. First, a quick, dense warm-up stage to get the indexer initialized with most of the other parameters frozen.
And then a much longer sparse training stage where the whole model learns to work with this new sparse pattern.
And the results show it worked. V3.2 performs just as well as the dense version on short context, and actually better on some long context reasoning benchmarks.
All while being cheaper to run on those H800 GPUs. They got efficiency without sacrificing power, a truly scalable base.
Okay, so that's the architecture. Now for that massive investment in post-training, the 10% compute budget.
That's an enormous number. But scaling RL is notoriously tricky. How do they approach it without the whole thing just becoming unstable and collapsing?
They use a two-step pipeline. First was specialist distillation.
Okay, what does that mean?
It means they trained 6 different specialist models, all fine-tuned from the V3.2 base. One for math, one for code, one for agentic search, and so on. Each one got a heavy dose of RL compute.
So they created these hyper-optimized experts in different domains.
Precisely. And then they used those experts to generate high-quality data, which they distilled back into one final consolidated checkpoint. It's a smart way to transfer all that specialized skill.
And the second step was the mixed RL training.
Right. Using an algorithm called Group Relative Policy Optimization, or GRPO. This basically merges all the training objectives, reasoning, agent tasks, human alignment into a single stage.
Which helps prevent catastrophic forgetting, where the model learns one thing and forgets another.
Exactly. But scaling GRPO itself is the real challenge. The paper goes into a lot of detail on the 4 engineering tricks they use to keep it stable.
And this is crucial because without this stability, that 10% budget is just money down the drain. Let's break those down. The first one was an unbiased KL estimate.
Yeah, this one is a bit in the weeds, but it's super important. It's about cleaning up the noise in your reward signal. They found that in really complex domains like math, the standard estimator gave way too much weight to low probability tokens.
So by correcting that, they made sure their huge compute budget was actually pushing the model in the right direction.
Correct. Then there was off-policy sequence masking.
This sounds like it's about dealing with stale data, right? When you're training on rollouts generated by an older version of the model.
That's it, exactly. They introduced a binary mask, MIDE, to basically ignore sequences where the model made a mistake and that were generated by a very different older policy.
So you stop learning bad habits from outdated failures. Makes sense.
Then, because this is a mixture of experts model, they had a specific challenge they called keep routing.
Why is that so important for a MOE model?
Because in a sparse MOE model, only a fraction of the parameters, the experts, are active at any one time. If an update changes which expert gets routed to, you get this mismatch. Keep routing forces the model to use the same expert paths during training that it used during sampling.
Which keeps the optimization process stable for that sparse architecture.
Yep. And the last one was the keep sampling mask.
This one's about top sampling, I assume.
Right. When you sample, you're restricting the vocabulary. If you don't apply that same restriction during training, you break some core assumptions. This just ensures the action spaces match.
So these 4 strategies together are what made it possible to actually use that 10% compute budget effectively.
They are the quiet engineering foundation that unlocked all that reasoning power.
Okay, let's pivot to the agent side. How did they get thinking and reasoning integrated with tool use without it costing a fortune in tokens?
This was a really clever and, honestly, simple solution. They call it thinking context management.
And the core idea.
The model's internal reasoning trace, its thinking, is only thrown away when a new user message comes in.
So if the model is just making a series of tool calls,
it keeps its entire reasoning context. So if a task needs 5 tool calls in a row, it doesn't have to rethink its plan from scratch every single time. It just continues its train of thought.
That must save a huge number of tokens.
A massive amount. But they do point out a catch. Frameworks that simulate tool calls by pretending they're user messages, like Terminus, won't get the benefit.
Right, because that tricks the model into resetting its context. To train this, they needed that agentic task synthesis pipeline you mentioned earlier.
Yeah, and the goal there was to generate tasks that are hard to solve but easy to verify.
How does that workflow work?
It's an iterative loop. An agent generates some data, creates some tools for it, proposes a simple task, and then just keeps making it harder and harder, adding new tools and constraints.
Like that trip planning example they gave. It wasn't just plan a trip.
No, it was incredibly constrained. Non-repeating cities and hotels, a budget that changes based on what you book. It's a really complex symbolic reasoning puzzle.
And did that synthetic data actually help with generalization?
It really did. An ablation study showed that training RL only on this synthetic data led to big improvements on totally different out-of-domain benchmarks. It proves their generation pipeline is creating genuinely useful, complex tasks.
And we see it in the final numbers. On Terminal Bench 2.0, the thinking mode got 46.4% accuracy.
Which was way better than the non-thinking mode's 37.1%. So the thinking clearly helps.
But this brings us to that tension you mentioned, the one that the special variant really brought to light.
Exactly. The fact that this top-tier gold medal reasoning often comes at the cost of generating a lot more tokens.
So the base V3.2 is already at GPT-5 levels of reasoning, but then they created DeepSeek V3.2 Special.
Which was the experimental version where they relaxed the length constraints and threw in more specialized math data. And the results were, frankly, stunning.
Gold medals in the IMO and IOI, that's unprecedented for an open source model, matching Gemini 3.0 Pro.
It is. But you have to look at the trade-off. To get that 2701 rating on Codeforces, Specially had to generate 77,000 output tokens.
77,000. And what did Gemini 3.0 Pro use?
Just 22,000.
Wow, that's more than 3 times the number of tokens to get to a similar solution.
It's a huge difference. And if you're the one paying the inference bill, that erodes a lot of the efficiency gains you got from the DSA architecture in the first place.
So the intelligence is there, but the cost to access that absolute peak intelligence is still very high.
That's the core tension. The special model shows the potential, but the official V3.2 release had to be more constrained to be practical and affordable to run.
They also found they had to manage context carefully, even with the 128K window.
Yeah, for long search agent tasks.
Yeah.
And it was fascinating that their simplest strategy, discard all, where you just reset the context when you hit the limit.
Turned out to be the most effective.
It did. It hit 67.6% on BrowseComp, which was comparable to more complicated scaling strategies, but way more efficient.
So to wrap this all up, DeepSeek V3.2 is this huge success story built on 2 things.
First, nailing the architectural efficiency with DSA. And second, unlocking that top-tier reasoning by scaling up stable RL and using incredible synthetic data.
They've absolutely raised the bar for what open models can do, but they're also upfront about the limitations.
Yeah, they still acknowledge a gap in broad world knowledge because they have fewer pre-training FLOPs overall.
That token inefficiency problem is still there. Requiring much longer reasoning chains is a real cost.
And for the most complex tasks, they're still a step behind a model like Gemini 3.0 Pro.
But the central point is proven. That 10% post-training budget, if you can stabilize it, can get you to gold medal reasoning. Which leaves us with a really fundamental question.
Right. When the special variant got that huge performance jump just by being allowed to think longer and generate more tokens, it makes you wonder.
How much more intelligence density can we actually pack into a single reasoning token? Is the next big leap going to come from finding trillions more documents for pre-training?
Or is it about fundamentally optimizing the efficiency of the reasoning process itself, so we don't need a 77,000 token chain of thought to solve an Olympiad problem? That trade-off between knowledge scale and reasoning efficiency, that feels like the defining challenge for the next generation of models.